So in this video lesson, we're going to have a look at magnetism. So we're going to start by talking about the different kinds of magnets, and then we're going to start to have a look at electromagnetism. So magnetism is really attractions between materials with natural or artificial magnets. Okay, so we're going to talk about natural magnets first, and then we're going to talk about artificial magnets. So there's some materials that are natural magnets. And for example, iron is one of those materials that has naturally magnetic behavior. Okay, and so when we look at the structure of a natural magnet, we're just going to draw it as a bar magnet for now. Okay, and so a bar magnet has a north pole and a south pole. Okay, now normally we're going to color in the north pole in red and the south pole in blue. Okay, every magnet has these two poles. So one is the north pole and one is the south pole. And even if you were to cut the magnet in half, what would happen is, so if we were to, let's just look at, if we cut this magnet in half here, we would not make a magnet that is only a north pole and only a south pole. What would happen is we would make these two pieces, and each of them would still have a north pole and a south pole. And so we would have been just dividing the magnet into two new magnets that also have a north pole and a south pole. So there is actually no way that you can make a naturally magnetic material have only one pole. There is always a north pole and a south pole. Okay, and it's just the way that the molecules and the atoms within the compound or within the atom, it's all about the arrangement of electrons. Okay, and so those naturally magnetic materials like iron and lots of other metals as well are natural magnets. It's all about the arrangement of electrons within that atom that causes it to have this magnetic property. Okay, so lots of metals are magnetic, but there are some metals that are not magnetic as well. Okay, now magnets have what we call magnetic field. Okay, and so when we draw a magnet, so we're just going to draw a bar magnet again here. So we'll have our north pole and our south pole, and we have these things called magnetic field lines. Okay, and so magnetic field lines actually come out of the north pole of the magnet, and then they wind their way back into the south pole of the magnet. And so that happens in 360 degrees around the magnet. And so these are called magnetic field lines. Okay, and so what happens is that this creates a sort of field that happens around the magnet. And again, this is happening in 360 degrees. And we're always coming out of the north pole and going back into the south pole. When we're within the magnet, that means that our magnetic field lines go from the south to the north. Okay, because they have to travel within the magnet so that they can come out of the north pole of the magnet and then go back into the south pole of the magnet. Okay, now one of the reasons that we know that this happens is we can actually look at some photos of what magnetic field lines look like when we pour iron filings around some of our magnets. Okay, so this is a picture here, just showing that when we pour those iron filings, you can see the direction at which there's lines coming out of the North Pole and then going back into the South Pole of our magnet here. It's coming out of our North Pole and then going back into the South Pole of our magnet. And I'm just going to add one more picture here that we're going to look at for those magnetic field lines. There we go. Okay, so when we're looking at this picture, again, we can see, so these are just bar magnets, and they have iron filings that have been just dropped on top of them. So we have a magnet that's made of natural magnetic material, and then we also are dropping iron on top of it, which we know is also naturally magnetic. And so we see this pattern start to emerge around the magnet where the material starts to bunch up near the poles of the magnet, and we can start to again see these lines that are traveling from, you know, one side of the magnet to the other. Okay, when we put magnets near each other, we get these sort of also odd representations of how different magnets will interact with each other. And so we can see that we've got some magnetic field lines here that are going from one magnet to the other because they're attracted to each other. Okay, so we're getting these like attractions between the different parts of the magnet. All right. Now, when we're talking about magnetic fields, so those magnetic field lines that we were drawing around our magnet, again, remember they come from the north pole of the magnet back into the south pole of the magnet, okay? Those are invisible to the human eye. Okay, the only reason that we can visualize them on a magnet is if we drop some magnetic material on top of it so we can start to see what they look like. Okay, but those magnetic field lines are creating the properties of a magnet that extend beyond its like physical structure. Okay, and so it's why, for instance, when you bring a compass near a magnet, the compass starts to turn in weird directions. And so it creates almost, think of it like, kind of like a force field. If you think about like a sci-fi movie, it's not exactly the same as that, but you can kind of start to think about it like that. It's something that extends beyond the physical magnet itself, so beyond the physical bar, and exists in the space around it. It still has physical properties. It's just really hard to understand because we can't see it happening. We can only see how it affects other objects when we bring it close to it. And so that's why I liken it to a bit of a force field. If you think about like in Star Trek or Star Wars, when they put up their like force fields or shields around their spaceships, it's that similar kind of idea where it's sort of this invisible thing that's extending out from our visible object. Now, magnetic field. So magnetic field has a symbol associated with it. And so it's a capital B, and it's actually a vector, okay? And so those magnetic field lines have specific directions, all right? And it's measured in Tesla. And it's from Nikola Tesla. Nikola Tesla did a lot of experimentations into magnetic field lines. And so the concept of magnetic fields, we get the unit from Nikola Tesla. And the unit symbol is just a capital T. Now, we're not going to work with a lot of calculations for magnetic field. That's in grade 12 physics. But I just want you to be aware that magnetic field has a symbol associated with it, and we do measure it in Tesla. All right. Now, our artificial magnets. Okay. Our artificial magnets are essentially brought to you via electricity. And so this is where we come up with the term electromagnetism. So hopefully you've heard of that term before. And essentially it means exactly what it says. It's the creation of magnetism using electricity. Okay. So when we run electricity through specific objects, we can create magnetism. So even an object that isn't naturally magnetic, we can make it magnetic by running electricity through it. It doesn't work for every object. It has to have still certain properties in order to make it an electromagnet. But lots of different metals that aren't naturally magnetic can be turned into magnets using electricity. So we run electricity through it, and then we're able to create an electromagnet. Now, the easiest way to do this, if you want to sort of visualize what an electromagnet might actually look like, is you could do this at home with a AA battery and a piece of copper wire, or really any type of metal wire. And you can actually create this yourself. So really all it takes is if you take a little battery, so if you take your AA battery here and you connect wire and leave the wire sort of coiled a little bit. And you can do this by having it connected just using a rubber band. So you can string a rubber band essentially around the battery to connect the wire to the battery. And if you do that, you actually should be able to pick up some metallic paper clips. So you should be able to create a magnet that will attract other metal materials to it. Okay. Now, when we are dealing with electromagnetism, we have to talk about the right-hand rules for magnetic fields. Okay, so when we're looking at electromagnets, they use the 3 right-hand rules. To govern our magnetic field lines. Okay, now most important thing about these right-hand rules is that you have to use your right hand. Okay, it seems silly when I say it, but lots of students will accidentally use their left hand. Okay, and unfortunately the right-hand rules only work if you use your right hand. All right, and so using the right-hand rules, we're going to have to actually use our hand to help us visualize what the rule kind of looks like. And so I'm going to do a separate video with some visualizations of my hand, just so that you can see the visualizations if you're struggling with them. We're going to just discuss them and talk about them in this video. So we're going to start with right-hand rule number 1. And right-hand rule number 1 is going to involve electricity through a straight wire. And so a straight wire really just means a thin wire like this that is relatively straight. It doesn't have to be perfectly in line. It could have a slight bend to it if you needed it to. It would still be considered under right-hand rule number 1 to be a straight wire. Okay. Now, with right-hand rule number 1, we have electricity going through a straight wire. So if our electricity in my wire that I've drawn here is going straight up, okay, we are going to be able to draw the magnetic field lines that are going to be around the wire. Now we're going to use our right hand for this. And so with your right hand, we need a couple of things. Your thumb is going to point in the direction of the current. And so in my right-hand wire, my wire that I've drawn here, this is my arrow. So that's my current direction. It's the direction in which the electricity is flowing. Okay? And so that's going to be my thumb. So my thumb is going to be pointing up in this case, okay? Because that's the direction of my current on the wire that I've drawn, okay? Now, when you point your thumb up, curl your fingers so that they're forming a little bit of a fist, okay? The direction in which your fingers curl tells us the direction of the magnetic field lines. So when I point my thumb up, my fingers curl around, okay, in this direction. So they're going behind, and then they're curling around this way. Essentially, they're curling around in a counterclockwise direction. Okay, so clockwise would be the way that the clock moves around. They're curling around in a counterclockwise direction. And so those are concentric circles. And those are from my curled fingers. And those concentric circles are representing the magnetic field lines. So when my current is pointing straight up, my fingers are curling around in a counterclockwise direction. And so that's the direction of magnetic field lines, okay, for that particular wire. Now, if instead, so say we have, let's do a second example here. Say we have our wire, only this time the current is flowing through the wire down. So that means that when I am positioning my right hand, my thumb needs to be pointing down, okay? And I'm going to have my fingers are going to curl around in a clockwise direction in this case. So they're going to curl around clockwise. So they're now clockwise in terms of direction. And so that's my magnetic field lines. So I'm going to show you a picture of what this sort of looks like. And so this one is showing, excuse me, this one is showing our first example here, where the current is flowing up through the wire. And we've got our hand in position here so that our thumb is pointing up, which means our fingers are circling around and we're going in that counterclockwise direction. Okay. If we have the opposite being true, okay, then what happens is our thumb is pointing down and now our fingers are curling around in a clockwise direction. Okay. When we are dealing with straight wires, there's another way to show a straight wire. Okay, and so if we show a straight wire with a circle with a little dot in the middle, this means that the wire current is coming out of the page towards you. If we draw the wire current with a circle and an X, this means that the wire current is going into the page or away from you. And this is how we're able to show our wire in not just 2 dimensions on a piece of paper, but rather in 3 dimensions. So we can be going up or down, or up, vertically or horizontally, but we also can be traveling on the Z axis into the paper or out of the paper. Okay, so if we have a wire and the current is traveling out of the paper towards us, that means that we would have to align our right hand so that our thumb is traveling towards us, which means that our circles are going in this counterclockwise direction. So those are our magnetic field lines going in a counterclockwise direction. If we have our wire that's facing into the page, that means our thumb has to be pointing into the page. that's going to make our concentric circles going in a clockwise direction. Okay, and again, it's all about placing your hand. You're using your thumb for the direction of the current, and then you're curling your fingers around, and the direction in which your fingers are curling is the direction for the magnetic field lines. Okay, so that's right hand rule number 1. Now, right hand rule number 2. So with the right hand rule number 2, we are having a look at electric current. Traveling through a solenoid. Okay, now a solenoid is just when the wire is in loops. Okay, so for example, rather than having straight wire, we have wire that is looped around in circles, and that's a solenoid. Okay, all right, now I can get you a nicer picture of a solenoid. You can put this one in here. Okay, so ignore the hand for now, but we've got a nicer picture here of a solenoid. If you look in the bottom right here, this is a solenoid. So you can see that the wire is just curled around, and it almost looks like a spring. Okay, we're gonna leave that picture for a few minutes. We're gonna come back to it. All right, so with our right hand rule number 2, we have electricity traveling through our curled wire. So our wire is curled up like a spring, okay? And so the electricity is traveling around in circles. And so with our right hand rule, again, we're using our right hand, okay? In our right hand rule, our fingers, so this is right hand rule number 2, our fingers are gonna follow the current. And our thumb will actually be the north pole of the magnet, okay? So if we have a wire, and the wire that I've drawn on this page here, I have the current is curling out of the page towards me, okay? Which means my right hand, my fingers are gonna look like they're curling out of the page towards me. And that means my thumb is pointed to the right. So that is going to be my north pole, which means the other side has to be my south pole. And I already know how magnetic field lines react when we have a north pole and a south pole. They come out of the north pole and they go back into the south pole. So they come out of the north pole and go back into the south pole. Okay, so then let's have a look at this picture. Nope, I'm gonna just add the picture again so that we can look at it again. Okay, so if we have a look at our solenoid, so we have electricity is coming from the battery and it's going into the solenoid, and then it's curling around before it comes back out, back into the battery. And so this solenoid again has the electricity curling out of the page every time, which means that our fingers, so if we're looking at our right hand over here, our fingers have to be curling out of the page. So then our thumb is pointed to the north pole, which means our north pole is on the right. Okay, and so that's how we're able to label the north and the south pole of the solenoid. And then we always know that magnetic field lines come from the north pole back into the south pole of a solenoid or of a magnet. Okay, and so that's how we use our right hand rule number 2. Okay, it's a little different than right hand rule number 1. Obviously, we're using opposite things in terms of our thumb and our fingers and what they mean. Okay, so right hand rule number 1 is with a straight wire. Right hand rule number 2 is with that curled wire or solenoid. All right, now our last one is right hand rule number 3. And right hand rule number 3 is actually a little bit different because right hand rule number 3 is actually an open hand rule. And this one is actually looking at magnetic force. Okay, so while in right hand rule number 1 and number 2, we are looking to find the direction of the magnetic field. In right hand rule number 3, we are actually looking to find out about the magnetic force that will happen to something that's in a magnetic field. Okay, a great example of this is that if you have ever had an MRI machine creates a magnetic field around it, and then you are placed in the MRI machine. Now, if you happen to accidentally have metal on you when you are placed in that MRI machine and the magnetic field is turned on, there will actually be a force on the wire or metal, whatever object you happen to accidentally have with you, and it will align itself with the magnetic field in the MRI. It's why they're extremely careful about making sure that you're not wearing any jewelry, making sure that you don't have like a pin or something in your ankle, because if you have metal, when they turn on the MRI machine, the magnet of the MRI will actually cause the metal to move and realign itself. And for example, if you happen to have a metal pin in your ankle, it can actually tear all the way through your ankle. And so because it will be aligned because of the magnet and the strong magnetism of the MRI machine. All right. So when we are using our right hand rule number 3, we're going to use an open hand. Okay. With our open hand, we're going to have our thumb is going to be the current direction. Okay. Our fingers will be the direction of the magnetic field. And our open palm will face the direction of the magnetic force. All right. So we are going to draw an example of this. So if we have 2 magnets, and we have these 2 magnets that are interacting with each other. So we have one magnet on the bottom here where the North Pole is up, and then a magnet on the top here where the South Pole is down. Okay, so magnetic field lines are going to go from the North Pole of one magnet into the South Pole of the next magnet. So that's the magnetic field. So we know that that's going to relate back to the fingers of our right hand, which means our fingers for our right hand in this specific scenario are going to have to point up, okay, because that's the direction in which the magnetic field lines are going. Now, if we put a wire in here, so I've got this wire that's sitting in here, and the current on the wire is going to the right, that means that my thumb is going to have to point to the right. Okay, which actually is going to mean that my hand is going to look a little like this. All right, so my thumb is pointing in the direction of the current. My fingers are pointing with the magnetic field. And this is going to be my palm. which means my palm is facing out of the page. That is the direction of the magnetic force. So the magnetic force is coming out of the page. So it's coming out of the page towards you. Now, I do have a better picture of this. So if we look at this picture, this is going to look a little bit better. Okay, so we have our magnetic field lines that are going up. We have current on our wire, which is going to the right. And so then that's going to mean that our right hand, our palm is facing out. And so that's the direction for our magnetic force. Okay, all right, those are the right hand rules. Okay, so those are how we can determine the direction of our magnetic field and how we can determine the direction of our magnetic force with right hand rule number 3. Again, I cannot stress enough, make sure you're using your right hand. All right, so that's it for this video lesson on magnetism. We're just looking at the different rules for magnetism. There is a bunch of practice for you to work on, as well as an assignment for magnetism. Okay. Also, I'm going to post another video just showing the directions of my hands, just so that you can see it